In our lesson goal for today, we'll be dealing with real numbers. Remember, real numbers are rational numbers, which include integers, whole numbers, and natural numbers, and are irrational numbers. When we have the square root of a perfect square, we have rational numbers. When we have a square root of non-perfect squares, we'll have irrational numbers. Our focus for this lesson is estimating non-perfect squares, irrational numbers. By the end of this lesson, I will be able to classify, graph, and compare real numbers, find and estimate square roots. That is our focus for today, estimating square roots. How can I estimate the square root of a non-perfect square? Please take a moment to answer the following questions. If this pattern continues, which will be the first figure to contain more than 200 square units? The first figure only contains 1 unit, the second figure contains 4, the third contains 9, and the fourth figure contains 16. Please hit pause and see if you can answer this one. One method would be to use times tables chart. 1 times 1 is 1, we have 1 square. 2 times 2 is 4, we have 4 squares. 3 times 3 is 9, we have 9 squares. 4 times 4 is 16, we have 16 squared, followed by 25, 36, 49, 64, 81, and 100. If we continue this, it would be the 15th figure to have over 200 squares. A number a is a square root of a number b if a squared is equal to b. An example, 7 squared is equal to 49, so 7 is a square root of 49. The radical symbol indicates a non-negative square root. When we see this square root, it will be a non-negative. That means positive numbers and 0. Also called a principal square root. The expression underneath the radical is called the radicand. Together, the radical symbol and the radicand form the radical. So again, what's the number underneath the radical symbol? That's your radicand. The radicand is A. The radical symbol is just a symbol, and when we put them together, we have a radical. Sometimes you could read this as the square root of 64, or you could simply say radical 64, which is 8, since 8 times 8 is 64. The square root of 81. The square root of 81 is equal to 9, since 9 times 9, or we can say 9 squared is 81. The square root of 225, we know that one is 15, just like in our example, the 15th term had 225 squared. Sometimes you may not know the answer, so then we use the most famous method for solving a problem, which is guess and check. I'll guess 17. 17 times 17 is 289, so that's too low. 18 times 18 is 324, so that's too low. 20 times 20 is 400, too high, so that means the answer has to be 19. 19 squared is 361, so the square root of 361 is 19. When we see a negative in front of the radical, this is read as the opposite of the square root of 25. When we see a negative in front of the radical, this is read as the opposite of the square root of 25. What's the square root of 25? It's 5. And what's the opposite of the square root of 25 then? Negative 5. This next one, we read it as plus or minus, not positive or negative. You have to say plus or minus. Please say plus or minus. Plus or minus the square root of 169, or plus or minus radical 169. So in this case, the square root of 169 is 13, and we just put the plus or minus in front of it. What do you guys think the answer for this one would be? If you said plus or minus 11, you are correct. And this next one, if you said negative 7, you are correct.
Pi, pi, pi. pi.
Sometimes your radicand is a ratio. In this case, since the numerator is a perfect square and the denominator is a perfect square, we can write them with separate radicals. The square root of 16 is 4, the square root of 25 is 5. So our answer is negative 4/5. In the next case, our numerator is a perfect square as well as our denominator. This allows us to write it as two separate radicals. The square root of 49 is 7 and the square root of 81 is 9. So my answer is plus or minus 7/9. But sometimes we have a situation in which the numerator nor the denominator is a perfect square. But that doesn't mean we can't simplify it. Notice that 8 and 72 have a common factor of 8. That means I can divide the numerator and the denominator by 8. And 8 divided by 8 is 1. 72 divided by 8 is 9 because 8 times 9 is 72. Now I have a perfect square in my numerator and my denominator. And the square root of 1 is 1 and the square root of 9 is 3. Please hit pause and try this next one. 20 and 125 have a common factor of 5. This means we can divide the numerator and the denominator by 5, leaving us with the square root of 4/25. The square root of 4 is 2 and the square root of 25 is 5. Unfortunately, you don't always know the perfect square. Where do we see irrational numbers in real life? Let's take a square that has a side length of 1. If we wanted to measure the diagonal, let's say we were at point A and we wanted to go to point B, we should know that the length of this line segment AB has to be shorter than going down street A than going up street B. That's why we're cutting across the field. And we also know that the length of line segment AB has to be longer than just one side. You could just use inductive reasoning, using your eyes to see that this red line has to be longer than this blue line. The length of segment AB is actually the square root of 2. The square root of 2 lies between 1 and 2. Irrational numbers will always lie between consecutive integers. Consecutive integers are integers that follow each other in order, like 1 and 2, 7 and 8, or 24 and 25. The square root of 2 approximately is 1.4142 ... It keeps going on forever. As you can see, 1.4 is between 1 and 2. We're going to estimate the two consecutive integers irrationals lie between. Let's take a look at the square root of 125 will lie between what two perfect squares? You should refer back to this chart. Notice that 125 lies between 121 and 144. Therefore, the square root of 125 will lie between the square root of 121 and 144. This means that the square root of 125 lies between the consecutive integers of 11 and 12. If we use a calculator to check our answer, we would be right. You should pause the video and determine what two consecutive integers the square root of 40 lies between. And this would be the square root of 36 and the square root of 49. Therefore, the square root of 40 lies between the consecutive integers of 6 and 7. Checking my answer with a calculator, I see I'm correct. The square root of 90. The square root of 90 lies between the square root of 81 and the square root of 100. This means that the square root of 90 lies between the consecutive integers of 9 and 10. Using a calculator to check my work, the square root of 34 lies between the perfect squares of 25 and 36. This means that the square root of 34 lies between 5 and 6. Notice that 34 is a lot closer to 36. That means the approximation of the square root of 34 will be a lot closer to 6, something like 5.7, 5.8, or 5.9. Using your calculator, you see that it's 5.8. The top of a folding table is a square whose area is 500 square inches. Approximate the side length of the tabletop to the nearest inch. When we take a look at this, this is saying that the area, the space inside this square, is 500 inches squared. If we want to find the side length, all we have to do is find the length of a side by taking the square root of 500. 500 is between what two perfect squares? You'll have to guess until you guess right, and that would be 22 times 22, which is 484, 23 times 23, which is 529. Therefore, the square root of 500 is between the two consecutive integers 22 and 23. The side length of the tabletop is between 22 and 23 inches. If you had a calculator or they allowed you to use a calculator, the square root of 500 is approximately 22.36 ... As you can see, 22.36 is between 22 and 23. Now, sometimes they make it a lot easier for you in this particular case. If they said that the area of the tabletop was 225, well, that would be a much easier problem. The square root of 225 is equal to 15. Therefore, the side length is 15 inches. This concludes our lesson for today.